Here's part 2 of that talk by physicist and engineer Ian Jamieson on quantum consciousness, leading to how dowsing may fit into the overall mind-bending picture of the universe from the perspective of modern science.
But I also want to point out a couple of things here. First of all, no light gets into the brain. Now, if we're just thinking from a physics point of view, inside our brain, there's no light. It's completely dark in there, except for the pineal gland, which gives off some bioluminescence, a little bit of bioluminescence, for reasons no one really knows. But inside the brain, it's completely dark. And yet our brain produces this big bubble of light on our shoulders, basically. So we have to realize, first of all, that the light that we see and perceive is something that's purely created by the brain, purely created by the brain. Light doesn't look like anything. It's a pure creation. Just as when a motorbike goes by, I think I mentioned this last time, motorbikes don't actually make any noise. They make waves, which we convert into an experience of noise. Our eyes convert what we perceive out there into an experience of light. But that is a pure reproduction. And people with synesthesia can often switch between those senses. So in other words, people can often hear music in color. Yeah. They visualize music, and some people can taste in shapes.
Right.
So these are just representations of the brain. So we have to realize that, put that in some context about when we try to come up with these theories, that we often forget that the brain itself is making hypotheses, and Piaget talks about this a lot, that the brain, and Hoffman, the brain is making hypotheses all the time about all this data that's coming in. It's getting huge amounts of data, and it tries to make sense of the world, and it finds correlations, which it turns into causations, and back to Hume and that sort of thing, these bundles of perceptions. And it comes up with a hypothesis. And that hypothesis is always tested all the time as a child. And it gets reinforced by certain experiences, reinforcement learning. And then you prune out certain other things that clearly weren't correct in your view of the world. And you gradually sort of evolve an understanding of the world. But it's still a hypothesis. We can't say it's true. It's still evolving as we get older, our view of reality. And particularly if you take psychedelic drugs or something like that, or meditate, you can get different versions of the world. So this goes back to the point. So I'm going off the subject a little bit here, but then you see, science thinks that our view of the world, we're looking out there and seeing an objective world, but it's not objective at all. It's a hypothesis of the world, and Hoffman calls it the user interface. And he says it's just like a user interface on a computer. It all looks fine and dandy, and we can use it and everything, but behind the scenes, there's a hell of a lot going on. That's the quantum processes that we're discovering, I think. We call them quantum processes. It's just reality, of course. So it's not unnatural then that if we view what we perceive as being reality out there, science goes on and tries to prove that perception as being reality, where it's actually a map. Our view of reality is a map of reality. It's, what a map is. It has certain features like contours on it. It's a model of reality. The map is a model of the outside world, and you've got a little map here that shows it. In our brains, we're producing a map of what we perceive as reality, but you mustn't confuse the map with the territory. And the problem is, in science, we think the map is reality, and so when we test things and everything, and we get a correspondence between what we test and what we think is right, well, of course, we're going to probably find out that they sort of match. And so it's no wonder that physicists who deal in the classical world sort of get a corresponding sort of, they confirm the map. Yeah. But they're using the map as reality. So it's, we get into those problems. Anyway, going back to the whole quantum thing. So in the quantum world, and there is this, in the brain, we've got a problem though, and von Neumann realized this as well. Even though it collapses, he said, well, what collapses in the brain? What exactly collapses the quantum perceptions that we might be getting, all these quantum possibilities. If it's not at the detector, it's not caused by the environment. A lot of people say, well, it's caused by the environment because the interact is called decoherence. But decoherence only decoheres into mixed states. Many theoretical physicists say, no, decoherence doesn't explain the collapse of the wave function into our classical experience. So it's not caused by those things. Decoherence will collapse superposition states and entangled states into mixed states. But they're still quantum states, but instead of and, now you have or, one or the other.
Yeah.
So that's setting that up. So I mean, these are subtle arguments. Let's look at Roger Penrose's idea about consciousness. The problem with consciousness in the brain, the collapse of the quantum possibilities in the brain, or having any quantum effects in the brain, is that it's a very warm environment. And warm environments mean there's a lot of interaction between things and you get decoherence. And so any superpositions will break down, possibly into mixed states. But then von Neumann came up with a mechanism for tackling mixed states called a density matrix, which is a bit technical to get into. But it doesn't actually, for all practical purposes, as they say, you can use a density matrix to figure out the probability of the most likely event to happen. But it doesn't actually explain where the collapse, what actually collapses it from many quantum possibilities into a single possibility of experience. That's just another technical point there. So the Penrose talks about, and so does Henry Stapp. So in Penrose's model, he really combines a number of things. So this might take a little bit of time. So I'm going to sit down for a second. So here's the thing with Penrose. He combines the idea, he says that the brain is not a computational, is not an algorithmic computational thing.
Right.
So he uses various methods to show that the brain is where the collapse takes place because it's non-computational. In other words, you need something to reduce. So he uses Gödel's incompleteness theorem to show that the brain can understand things that an algorithmic computer cannot.
Okay.
Right. He talks about mathematical truth. So, for example, Gödel, who was a brilliant Austrian magician, Gödel was a Platonist, and he believed in the transcendental world of, Plato's realm, the world soul, and that sort of thing. And Plato believed that things like the archetypes existed up there, like the perfect circle, the perfect forms, and that humans were the way of bringing down the transcendental world into the world we perceive. And of course, the allegory of the cave, that in the cave you see the shadows on the wall, and it's actually the light projecting your shadows onto the wall. We live in the shadow world, but the true world is this is Plato's cave, is the light, the light, where the light is coming in. But our bodies basically are sort of amplifiers of the transcendental world into the immanent form. So he believed in that sort of idea, and Gödel was able to show, using a form of meta-mathematics, that there are mathematical theorems that no algorithmic logical process can actually prove to be true. However, he also showed, or he also explained, as Penrose, and Penrose is also a Platonist, that mathematics, that human intellect can actually, by looking at a problem, so the mathematicians say often they go into this transcendental sort of world when they're thinking about a problem, and they can actually see it, they can actually show it to be true in their minds. They can understand it to be true, but no algorithmic computer can show it, can prove it to be true. So humans can know things that an algorithmic process cannot. And so Alan Turing went a bit further, and with his using this universal Turing machine, he showed that if you're trying to solve a problem with an algorithmic machine, which was called the universal Turing machine, that you never know if it stops or not. And it's by stopping it solved it. But you can never know if it's ever going to stop. You could wait the end of the universe. And his proof, along with Alfonso Church, it's called the Church-Turing hypothesis, actually shows that there are numbers that no computer can generate. Now, we don't know what those numbers are, but they're able to show, and they use basically a very similar process as Cantor used. Cantor, of course, a great mathematician, that he used the diagonal procedure to show that there's many different infinities of numbers. There's different infinities of numbers, and they use that sort of diagonal matrix, the Cantor diagonal matrix, I think it's called. Anyway, so there's this idea from Turing and from Gödel that there are, there's mathematical truths out there that cannot be algorithmically proved by a computer or any other algorithmic method, but the human brain, for some reason, can understand them and understand that they are mathematical truths. Gregory Chartan at City University in, I think it's at City College in New York, he's actually gone a step further, and he's shown that actually there's mathematical theorems out there that not only cannot be shown to have a proof algorithmically, but don't have any proof. In other words, they're completely random mathematical theorems that the human mind can know to be true, but they don't have any logical reason to be true. And it's that people say it's the mathematical equivalent of the Heisenberg's indeterminism, uncertainty principle, that mathematics also has an equivalent of that. Anyway, but the human mind can know these things, whereas the machines can't. So Penrose is basically saying that that there is something that happens in the brain that's non-computational, and he believes it's the actual collapse of the wave function of all these possibilities. Now, he points out you can't just do a random collapse of a universal Turing machine and have the same effect. You can't give, if you had a bunch of universal Turing machines all parallel processing, like the brain parallel processing these quantum or a general quantum machine, parallel processing something. You can't just put a random event in there and have it collapse it and then have this reduction of the quantum things. It doesn't work that way for various technical reasons. But in the brain, somehow there's a nonlinear event that happens that all these Schrödinger evolutionary deterministic evolution of all these possibilities in the brain of the sensory data that comes in, the possibilities of it, is collapsed into our one experience of one of them. It's reduced. The wave function, the evolutionary, deterministic evolution of the Schrödinger equation, describing all the states of the brain, is collapsed into one state that we experience. Now, how does that happen? First of all, how does Penrose go about saying that there is this quantum superposition of all these states in the brain, given that the brain is a very hot and wet place? He explains it, first of all, so there's two parts. He has to explain that, and he has to explain what actually does the collapse. I'll explain both of those. So the first one is using the idea of Stuart Hameroff, who's an anesthesiologist, professor of anesthesiology in Arizona, I think. He's a practicing anesthesiologist. He's written a book on this. He says that in the brain, there's these things called microtubules, which are the cytoskeleton of a lot of cells, and including the neurons and the axons and dendrites. The axon is the transmission thing, and the dendrites the input to the neuron. And between them, there's this synaptic cleft, which sort of mitigates between those two things. And it's got the neurotransmitters in, like serotonin and dopamine, and that's 200 different neurotransmitters, of which I know 2. So those are the ones I know. So all these cells have this structure, this microtubule, which is these little. They're very small, and they're made up of a protein called tubulin. And tubulin is a dimer. It can transform its protein shape between two conformations, alpha beta, of this particular dimer. The other thing about the microtubule is that the shape of it is like a sunflower, and say it's made up of the Fibonacci series. The adding numbers like 1 + 2 is 3, 3 + 2 is 5, that sort of thing. And so they think that in these microtubules, the other thing is filled with visceral water, which is a very ordered form of water. That's all I'll say about it. That's as much as I know about it. So these two things, the fact there's the Fibonacci thing involved in there, the fact that they're very long and they're like a waveguide for electromagnetic fields. They sit in cells, and they can actually shield the electric magnetic field. So they shield it from the any outside decoherence, basically, of the superpositions of all these different possible things. So even though the brain can be in many different states, it can exist in these superposition states through these microtubules. And since it can conform into two different states, you've got two possible states there that can be in actually quantum superpositions of the different conformations of the tubulin in there.
Okay.
So that's the way he sort of explains how you can still maintain a big coherent system in a sort of very hot environment.
Right.
Now, so now he's explained how you can possibly have these the superposition of very different mental states in the brain going on. How does he explain the collapse of all these different superpositions of possibilities of what our actual experience is into one thing that we actually perceive, our actual experience? Well, he does this by saying, well, he believes it's actually quantum gravity that causes the collapse of all these different quantum superpositions. Now, how does he explain this? By the way, the Penrose model is the easier one to explain rather than the Stapp one I'm going to explain. Just to give you a sort of heads up there about what's coming. So he says that when the energy difference between the different superposition states, so you might have one state, let's just look at a pair. So you might have one particular thing that's saying you're going to run away, a flight or fright. So two different possibilities. One state telling you to run away, one saying to fight. When the energy difference between these two states is significant, what it creates in space-time is actually a state that when you have to deal with quantum gravity, you have to say that now you've got a superposition of two different conformations of space-time. You've got a space-time with this energy in it, and you've got a space-time with this energy in it, and they're overlapping. So you've got a quantum superposition of gravity going on there, because energy and mass are equivalent, sort of thing. And he's been able to put some numbers on this and show that it's actually quite reasonable. His thoughts are quite reasonable. And so what it does, he says, at that point, when the energy becomes, the difference between the two states become a certain amount, you're going to collapse. You don't get an algorithmic collapse, you get a nonlinear sort of collapse between things. And he points to the idea of Hartle and Gurok, who are two physicists who've come up with a different quantum gravity sort of theory. And they say that when they discovered that when they try to use topology to reduce a four-dimensional surface, and topology is basically taking a shape and you can maneuver it into different other shapes without cutting it or breaking it. Yeah. They say that when you deal with four-dimensional space-time and try to reduce it in some way to into another configuration, there's no algorithmic way to do that. It's actually too difficult for an algorithmic way. So there must be some non-algorithmic process that goes on where you can reduce the four-dimensional space-time into a different conformation. Basically, that's what they're saying, a little more technical than that. So he says that there must be some sort of way that the universe deals with having two different structures of space-time in one place and reducing one into the other. So he thinks it's actually the space-time is the universe as a whole collapses the space-time geometry of the universe. That collapses. Okay. It doesn't like having two different things. It collapses it one into the other. So that's the reduction. That's where the reduction of all these different quantum states happen. It's by the geometry of space-time itself, the whole universe being involved and saying, yeah, I don't like this having all these different states. I'm going to bang, that's it. We've got the one going on. That's basically Penrose's model. So he takes the wave function quite seriously, but he also says about that basically he goes back to the Platonic thing, saying about the Platonic realm where humans actually project those forms into what our experience of them is somewhat a more physical realization than the actual transcendental realm, which would be the quantum realm into the classical realm sort of thing. That's the Penrose one. And I can go through and explain the Stapp one. It's more technical and difficult, but it's probably the one that's more in line with your quantum dowsing.
It is. Oh, okay. Okay. Oh, I was really. I'm ready. I'm gearing up for this one. Okay.
All right. Okay. Here we go. Henry Stapp, brilliant theoretical physicist. So Penrose, Stapp, the giants of the quantum world, the quantum theory world. So I explained about the de Broglie world. I explained about Heisenberg with the idea of potentia. I've explained about von Neumann. So we got through that stuff. So we should be, and I explained that there is a difference between a quantum superposition and a mixed superposition. I should just add to that a little bit, that when, like with the silver mirror and everything, and with the qubit, if decoherence happens, then what happens is that decoherence doesn't explain how we go from a quantum world to a classical world. What it does do is it goes from the quantum superposition, where it's this state and this state at the same time, a particle can be in both states at the same time, to a quantum mixed state where it's one or the other, but it's still a quantum, it's still a cloud. Now, if you take the evolution of the universe as a whole, then if there was no universal mind, and I'll come back to this, there's no one observing, if humans weren't around, let's say, or a conscious observer, then the universe would evolve in the Schrödinger typical evolution, deterministically. All the possibilities will just be smearing out. There'd be a multiple smear of possibilities. It's called a quantum smear. It's also called it can also be called a quantum statistical mixture, because they're all mixed together. All right, a statistical mixture. Now, there is a difference between a mixed orthogonal mixture. A mixed orthogonal mixture, as far as I understand it, as far as the Stapp sort of explains it, and my understanding of it, is that if someone came along and asked a question of it, like, okay, if I look at this thing, will I get a yes or a no, like in the mirror thing?
Yeah.
So an instrument does that. And Heisenberg said, remember, the universe reveals itself in the questions we ask it.
Yeah.
You put a detector in there, am I going to get a photon or am I not? And so here the thing is that when you do that, putting the detector there, you can also get just a quantum mixture from the answer, yes or no. So in other words, you'll get an orthogonal mixture. So in other words, it goes from a statistical mixture where you might get an answer yes, no. It can be yes, no at the same time, to one where you're going to define it. You're going to reduce it down to yes or no. And that would be, but that yes or no will actually correspond to a classical observable.
Right.
A classical observable, yes, I see the photon coming through, no, I don't, that sort of thing. Whereas, yes, I see it coming through and I don't see it coming through.
Yeah.
That would be a mixture, whereas the other one would be, the orthogonal would be corresponding to something we can experience. Yeah. That's an important point. That's an important point to make for Stapp's. I'm giving you a ton of information here. I know it's difficult. I apologize, but to understand his theory properly,
it's fine.
It is a difficult theory.
Yep.
I have to be very exact about these things. So let me have a go. Von Neumann, when he did his analysis, going through here, so Stapp uses Heisenberg and von Neumann sort of explanations. Okay. So when von Neumann was looking at this, and he looked at the what goes on in the brain, he says there's a number of things happen here. First of all, when the quantum superposition of all the possibilities that we might collapse. So in other words, we are, if you like, when we look at the instrument, we're sort of connected with that instrument. We're part of that whole wave function, if you like, that describes all of those different things. Now, what collapses down? So we're going to perceive the instrument as giving a yes and giving a no, whatever. Now we're sort of our brains are like a quantum superposition of that. So we can explain this from a slightly different point of view as well. That in the axon that comes down to the dendrites, there's a synaptic gap. right, from a neuroscience point of view.
Yeah.
And as the signal flows down, it goes into the bouton of the little bulb at the bottom of that connects across the synaptic gap to the dendrites on the other side from one neuron to another. The signal goes in, and what it does, if it's significantly strong enough, it will send out little calcium ions down what's called an ion channel. The ion channel is very narrow, and so it's actually just a bit bigger than a calcium ion. You know, calcium ion has got the charge on, and so it spits it out very fast. But because of the narrowness, just like with the slits, it causes the calcium ion to be an uncertainty about when it comes out. The calcium ion goes across, and it hits these little things in the bouton called vesicles. The vesicles contain the neurotransmitters. So where it actually hits them, and if it hits enough of them, there's actually only a 50% probability of it hitting one or something and actually producing these things that then go across the synaptic gap to the other. And if there's enough neurotransmitters to go over there, it will pass the signal. So there's a quantum event going on there as well. And so we've got these different quantum events, and I might just simplify these things. But anyway, so there's these quantum possibilities of what can happen in the brain. Not only are we connected with the device, there's these other quantum events going on. I don't think we have to worry too much about those things, but they're all part and parcel of his explanation. Now, the point that von Neumann made is that he said there's two parts that go on the brain. First of all, the process 2, he calls process 2, which is the deterministic evolution of the wave equation, which says all these probabilities, even in the brain now. So the whole system comes into the brain with pointed this way and that way. And then there's, you get this spread of all these different possibilities because of all the quantum effects at the synaptic gap. So you get all these different possibilities happening. So you've got this smear of probabilities in there. So how do we sort out that smear of probabilities? Well, von Neumann said there's a process 1 now that comes along. And he says that we ask nature a question. When I say we, he says our mental intent. Our mental intent asks the question. And this is the important part. He considers that there is an actual separate mind that has intent to ask nature a question. And this is important when it comes to the dowsing thing, because we ask nature. I remember you distinctly saying about asking a question, right? Of the divine ones. Yeah. We ask a question. We ask the question, am I going to, the fight or flight? Yeah. Two things. Am I going to run? Am I going to stay? We ask a question, our brain says, should I run? Should I not? Yeah. Right? So there's right there, no longer are we deterministic beings. William James said this about the stream of consciousness, and it's not a classical thing. There's something about our brains that gives us the ability to affect the world. For example, I used to do in my physics lab all the time. I used to have a 1 kilogram weight on my bench, and I used to say, I can move that weight with my mind. No, that's sort of the usual. You got a magnet under there. No magnet. So I just go and pick it up and move it like that with my arm. And they said, well, that's cheating. I said, no, I said I moved that with my mind. I did. I moved my arm with my mind, and I put it over there, and I moved the thing. I've just moved that piece of matter with my mind. I've affected the universe by doing that. So anyway, so the mind does the same thing. How does the mind move that arm? How does it start to move my legs to run? This is where the quantum Zeno effect comes in as well. Now, this is going to wake you up. So stay with me here. So what was that? Process 1. So it's a process 1 now that comes in, where we ask nature a question. We say, am I going to experience running away, or am I not? So that's where the mental question comes in. But what answers the question? Von Neumann and Dirac both said nature answers that question. Nature answers. The management answers.
Yeah.
If it's within their will, so Stapp was saying it's basically the universe as a whole answers that question. They say whether it's going to be yes or no. But you've asked the question, you see. And nature makes a decision on that yes-no thing. So process one is made up of two parts. It's made up of your brain asking a question, whether subliminally or not, it's somewhere in the brain, something's going on, and there's a question being made: do I run? Do I stay?
Yeah.
Which happens is determined by nature. Somewhere, the big universe makes that, and I'll explain how that happens in a minute as well. Well, I'll see if I can explain. So Stapp will explain. So that collapses the wave function. We get an experience of fight or flight. Now, how does that mental intent transform into actually just running or not running? Well, Stapp says that basically we have these templates for action that have been built up over time. We evolve to, as children, have these templates to run or to stay or whatever. We know what running is. Our brain knows what if it's given a command. So so basically one decision is going to be made. It's going to be yes or no. The templates for that action are already there. So the collapse comes, oh, I'm running, I'm going to run. What happens is that template's there. How does it continue on in a quantum way? It's still got there's still a quantum phase to this in the sense that the particles in the brain are quantum. So how does our mental intent transfer into a physical action? He says it's basically through the whole idea of the quantum Zeno effect. Now, Zeno was actually a student of Parmenides way back in southern Italy, and Ilya, or Ilya, I can't remember now. But he came up with the idea of, if you want to go from A to B, you have to go halfway from A to B. And if you want to go from A to halfway to B, you have to go halfway from A to halfway, so forth, so forth, so forth. And so you keep dividing in half. And so he said you'll never actually start because you always never get to that halfway point between the halfway point to the halfway point to the halfway point. So, and it's also the quantum, the Zeno arrow. If you fire an arrow, if you look at a particular moment, you'll actually stop it because, it never actually moves.
Yeah.
So the quantum Zeno effect, the Zeno effect of that, there's two. There's the quantum Zeno effect and the quantum anti-Zeno effect. Stapp's written papers about this and they're very technical. But let me just explain about the quantum Zeno effect for keeping an action in place. So it's been shown that if you keep observing, now a quantum system will evolve. Right. Will evolve in a way like the particle going through. The probability of spread will spread as time goes on of where you're going to find it, quantum cloud. But if you keep observing, if the brain keeps observing that cloud, it will fix the intent. So if your intent is something, I shouldn't say it fixes the intent. If your intent is something, the observation, this is why meditators are much better at these paranormal sort of tests and everything. If the brain keeps focused on something, it will keep that template for action activated. Right. It keeps observing it. So the quantum state of that template, the yes one over the no one of not running, there still might be a quantum mixture, those two things. It'll keep that going. It will keep that, and it'll show you keep measuring it, you're going to keep it in the same state. And so that's why it will keep transmitting that intent. The watching of it, the observing of it, will keep that brain state going. That brain state is activating your flight mode. Right. All right. So that's one way the quantum Zeno effect actually works in the intent, our observation, and mental observation of this particular template, keep it in action. Now, how does it move? How can you move the anti-quantum, the anti-Zeno effect? Well, I don't know if it's called the anti-Zeno effect in this. I think it is the anti-Zeno effect, but Stapp isn't exactly clear. That there is evidence in the quantum world that you can actually, by observing it at a different rate, and there's a lot of math behind this, of course, that's been shown to hold, that if you observe it at a different rate, at a different sort of rate, you can actually move it from one state, a quantum state, to another. It's been shown with decays. So you can make a decay rate much quicker, even though it's random, by observing at a certain rate. So he says that you can essentially move the quantum state of which action template you're going to use, the yes, fly, run, no, don't, you can actually move it to the yes state with observing a certain rate as well. It's like the anti. So in other words, it's just like you can move the arrow from where you shot it to the other end, because when you sum, by the way, the mathematics behind the Zeno effect, they can show that with the Zeno effect, if you in the limit, as you add up all those fractions, so you've got infinitesimal fractions up to halves, and that, if you sum all of those in the limit, it becomes 1. So it does actually get there. So from a mathematical point of view, you can show in the limit it does happen. In the same way, using the same thing in quantum theory, if you observe it enough times over that time frame, you can actually move the state from one state to another. That's what Stapp is saying as well. So the whole Stapp thing is basically that he really talks about mixtures in the brain rather than superposition. So he doesn't have the same problem with it's already been decohered. And so he doesn't have to maintain a big coherence. And he eventually is able to collapse the wave function through 2 different processes: the intent of asking a question of nature, yes or no, and then the universal nature collapsing. How does the universal nature thing work? Well, he sort of evokes Whitehead's idea of the universe, of that every particle in the universe is basically, Alfred North Whitehead in Process and Reality is really the becoming of the entire universe. And through a process called concrescence. Process and Reality, the book is actually a very complex book to read, very hard to read, worth reading, of course. But he talks about this concrescence, the becoming of each individual particle. Each individual particle, it's a bit like Bohm's theory is a little bit similar. And of course, you get little pockets of concrescence, and then you have to tie them all together. But there's a better theory. So when it comes to the reason I mentioned relativity before is because in special relativity, you have this smooth surface of nows that sort of evolve through the universe, and you can have multiple nows and that sort of thing. So when you combine special relativity with quantum theory, you have some issues because because of many things. In relativity, you just have this one now, and you also have point particles events. So to get around it, Tomonaga and Schwinger came up with relativistic quantum theory, which allows for quantum events like entanglement to so with entanglement, explain entanglement very quickly here, that 2 quantum particles are entangled. If you change one, instantaneously the state of the other, when you measure it, changes as well. So it could be across the universe as soon as you change this. But relativity says no signal can go faster than the speed of light. So what's going on here? How can relativity, which says you can't have signals going faster than light, sort of mesh in some way with quantum theory? It says, yes, you can have these instantaneous information. Well, the way you get around it is sort of saying, well, there's no real information going between the two. It's because the measurement in quantum theory is a completely random event. What you're going to get if you measure something, you're going to get a random up or a random down. It's nature's deciding what happens. So a way to get around this with Tomonaga and Schwinger, they came up with relativistic quantum field theory, which won't go into here, obviously. But it says that basically, so you have these pockets, if you like, of there's not a smooth now anymore. There's different nows,
right.
And so a collapse of a wave function in one now classically would not be able to connect with another information. So if I experience something, if I collapse the wave function for something in an area, what's happening to the rest of the universe? In other words, if there was no humans, what would be collapsing the state of the universe? There must be a universal mind out there continually observing the universe. Well, it's a similar sort of thing here. That so these little pockets of experience can be us. So in our little world here, we might collapse the wave function, be looking out the window, and nature's saying, okay, yes, you're going to see that branch moving in that direction, or branch falling off a tree or something. How does that get sent to all the other little pockets of, because they're out of my now bubble, they're out of my local thing, But I want this to instantly happen across the universe. Well, it happens with a non-local connection between all these pockets, these nows, these individual nows are connected through entanglement. And so we pass my collapse of my local, the branch off the tree with all the rest. So anyone in the universe who was observing that tree would also see a branch fall off. It might take them a while to see it through light, but instantly the universe as a whole collapses it. So it's a bit like a universal mind. So it's like the Platonic realm, really, you think. I was going to go over Amit Goswami's idea of it, but we haven't got time. It's a very good one as well. But
we can talk about Amit Goswami another time.
So let's finish up quickly with the dowsing thing. So the dowsing thing could be explained by subtle quantum fluctuations, energies in the ground state of the universe, quantum field or something, and the body amplifying that, but it's still a superposition. And we're always amplifying these things by entanglement with the environment and everything. And so we bring it up to a level now, an energy level, if you like, and we ask the question, can you tell me where the water is under the ground, or something like that? Is it here? We're continuing asking, is it here? And our minds might be intent. If we're very intent on it, we could be saying all the time, is it here? Yes, no. Is it here? Yes, no. Eventually, our brains will say yes, like the flight one. And then we've got this action template which we learn. As we get better at this, learn it. That template becomes stronger, and it actually activates a signal, a very subtle signal, maybe in our hands, that tweaks the rods over and gives us the thing. But remember, the final thing that collapses it into one template or another is the quantum Zeno effect can do it somewhat, but the thing that makes the final decision is whether the management, the universe of mind is okay with it. Collapsing. So you can sort of see that the two sides of the coin there, the spiritual side, if you want to think of it like that, they sort of come together in some way. So I think that this sort of explains that, because it puts our brains are no longer just mechanical things. It doesn't explain where the intent comes from.
The way to say, well, where does the intent come from, is that whole spiritual perspective of we are only existing as human beings and experiencing the three dimensions because the universe is trying to explore itself. So the universe is constantly asking questions of which we are only anyway at any one point experiencing one particular question being asked, and that actually creates the sensation of being alive anyway as an individual human being, which we're not. We're part of the whole universal field expressing a certain...
And actually, that's why I wanted to explain Amit Goswami's thing, because he actually says something very similar to that actually it's the universe observing itself in many ways. That our intent comes from the non-local consciousness that asks the question of itself, and this sort of feedback thing. So he actually came and taught my class once or twice, and I've met him a number of times out in Hawaii. And he's really good, very smart, gave lectures out there. And his book is called The Self-Aware Universe.
Yes,
it's really worth reading. It's very clever. And he draws on Escher and his idea of the drawings and everything. So it's really very good book. So
it is an excellent book. That's one of the few books that you mentioned that I have actually read, and it is the only book on quantum physics that actually made me cry at the end of it.
Really?
It's so wonderful. I mean, is there anything that you want to add to your amazing monologue?
I missed it out. Oh, I did want to say, there's a great quote by Lyle Watson I really love. I've got to say, he wrote Supernature called, and it's if the brain was so simple we could understand it, we would be so simple that we couldn't, which is actually a nice way of putting Gödel's incompleteness theorem. If we're in the system trying to understand a system, it leads to all sorts of innate uncertainties or indeterminism, and therefore we find it actually hard to explain, or we have to explain it in very strange terms. Basically, the other thing I wanted to say is a point I wanted to make earlier on about this thing that the brain gives us our representation of reality. you know, whether it's a visual representation or an oral representation, and the, you know, synesthesia shows that these can get mixed up and everything, so they're just representations. Really, when you think about it, when you really think about this, it's quite an amazing thought to come to at times. My realization of this came at one point, is that we're actually just walking around inside our brains.
Yes.
So when we walk outside, we're actually walking around in this virtual reality our brains have created for, but we're not really walking. That's the funny thing.
Of course.
Even our bodies are creations. We're just thinking we're walking around in this field.